Hello and welcome to our webinar, Thermal Management Crisis, Knowing Your Passive Solution Options. I'm Lisa Riga with TechBriefs Media, your moderator for this program. Joining us today are Dennis Pamukchu and Ryan Spangler from Advanced Cooling Technologies. Dennis works in business development and product design and has more than a decade of experience in the thermal engineering industry. Ryan is a lead product development engineer, handling all design and development efforts in the company's defense and aerospace group. Today's webinar will include a Q&A. Please send your questions through the Ask a Question box on the screen. And now, please join me in welcoming Dennis Pamukchu, who will be giving today's presentation.
Good afternoon. My name is Dennis Pamukchu. I'm the Lead Business Development Administrator here at Advanced Cooling Technologies. Today we're going to talk about what are some passive solution options for managing your thermal crisis. Before we begin, I'd like to talk first about what is passive thermal management. When we talk about passive thermal management, we're talking about systems in which no additional energy input is required into the system in order to move, transfer, and dissipate your thermal loads. Typically, this involves natural convection off of heatsink assemblies and/or conduction through base metals. When we talk about an active system, now we're including elements such as fans, thermoelectric modules, and fluid pumps. These are good examples of active components that are going to draw power from the system in order to move, transfer fluid and/or air in an effort to solve your thermal challenge. So the benefits of a passive thermal management system are multiple. First off, by reducing the number of active elements within your system, including pumps, fans, thermoelectrics, you're reducing the complexity of the design. Removing these elements from your system has a twofold benefit. In addition, it will improve the mean time before failure of the overall system, improving the life that you're able to offer your customers. Passive solutions typically require less maintenance than their active counterparts. For example, there are no filters to clean, no pumps to maintain, no fans that can seize and need to be replaced. And finally, one of the other ancillary benefits of a passive system would come in the form of reduced energy consumption. Again, if we can solve the problem and allow it to operate in a passive way, now we don't have to input additional energy into the system to remove our thermal loads. We can focus that power budget on elements that are more function related. So in passive thermal management, enhancing conduction is one of the keys to developing an effective system. In most of these electronics cooling applications, the ultimate heat sink is going to be air. Whether this is a natural convection or forced convection heat sink, whether it's a pumped liquid loop that eventually dissipates its load to air, the more air you can push through the system, the more heat transfer is going to occur. Another important element to think about in terms of passive thermal management systems is that the device is never going to be cooler than the ambient temperature. Now, this is well accepted in a lot of electronic system design, but it's important to note that in some instances where you do need the inside of an enclosure to be cooler than the ambient environment in which it exists, you're likely going to need to consider an active solution at that stage. So what I'd like to do now is dive into the first tool that we're going to talk about as a passive option when designing your system. And this is going to be discrete heat pipes. So the first electronics packaging crisis that we run into a lot here at Advanced Cooling Technologies, when we have customers that come to us, whether from the packaging side, the design side, the electrical side, the interior of electronics enclosures that they are designed to be sealed from the environment in order to prevent dirt, debris, dust, liquids from entering and contaminating and or destroying those electronics. Sealing these enclosures is a great way to do that, but it also seals them from the ambient air outside, creating an oven-type environment in which your electronics are going to continue to generate heat and continue to rise in temperature until they reach some steady state. Now, as package design engineers, you're typically being pushed to decrease the size of the enclosure in an effort to reduce weight or to make it package better into your next level assembly. What you're doing essentially now is reducing the space for that natural convection. You can think of laptop computers now versus the counterparts multiple years ago, where you had a lot larger devices, but smaller power loads. Today's laptops have a very small footprint, very thin device, while packing much more power than what we saw years ago. Really, all of this has been achieved through enhanced thermal management within these types of systems, and we'll talk about now how heat pipes have benefited that. So a heat pipe is a passive two-phase heat transfer device. When we talk about heat pipes in the context of electronics cooling, we're going to be talking about copper water heat pipes. There are heat pipes that operate across a variety of temperature spectrum. A copper water heat pipe operates well in the temperature regime we typically want to operate our electronic devices, from 0 degrees C essentially all the way up to 150 degrees Celsius. A heat pipe is made of three main components. There's an envelope material. In the case of a copper water system, the copper refers to the envelope of the heat pipe. There's a wick structure, which is responsible for allowing the heat pipe to transfer its power in multiple orientations. That wick structure you can think of as a copper sponge in the case of a copper water system that gets sintered to the inner diameter of that envelope. And then there's a working fluid on the interior of the heat pipe. When we make a heat pipe, we're sealing these systems. We're pulling a vacuum and putting the small amount of that working fluid on the inside. What this ensures is that that fluid is operating along its saturation curve. So any heat input, even that of you holding it in your hand, causes the fluid inside to vaporize, and that location where that vaporization occurs we call the evaporator. So vaporization occurs at the evaporator. The working fluid now as a vapor travels down the pipe to a cooler location where it will condense and let out its latent heat. The area where it lets out its latent heat is called the condenser. The wick structure then transports that condensate back to your evaporator, and that's done passively in its own small closed loop. Essentially, a pressure differential caused by the temperature differential across the pipe causes the passive capillary action that drives the heat pipe to operate. A properly designed heat pipe is almost like a thermal short circuit in your thermal resistance network. So what I mean by that is where you might have a multiple degree, 10 to 20 degree delta T through a traditional base metal, a heat pipe effective conductivity being 10,000 watt per meter Kelvin and higher ensures that when you integrate it into your assembly, you're creating a thermal short circuit. An ideal, appropriately designed heat pipe should have no more than a 2 to 5 degree delta T across the length of it. So now we talked about what a heat pipe is. How do we use them? Heat pipes can be integrated into your assembly, again, to help move and spread heat. Because of their performance, because of the two-phase performance, heat pipes are capable of accepting heat flux up to 50 watt per centimeter squared. They're reliable. They've been used in a variety of applications and a variety of environments. Heat pipes have been in your laptops, as you know, now for decades. They've probably been in your cell phones to some extent as well. Here at Advanced Cooling Technologies, we focus on a lot of the very high power applications for both ground and space systems. So our heat pipes are designed to be, again, freeze-thaw tolerant. The way we do this is the wick structure on the interior of the heat pipe that we talked about previously needs to be able to soak up all the working fluid on the inside of the heat pipe. Overcharging a heat pipe with too much working fluid is a good way to ensure that when it freezes, you'll have fluid bridging the gap across the heat pipe, causing it to bulge when you do freeze. Heat pipe are also shock and vibration tolerant. The heat pipe itself can be subjected to shock and vibration without concern. Typically, what we see is the next level assembly is where you need to take a look at how the heat pipe is attached in order to ensure that that assembly is going to be shock and vibration tolerant. So now we have an idea of what a heat pipe is and where they're used. Let's talk about some of the design inputs that you need to understand in order to actually design your own heat pipe system. The first input is to understand the amount of power that you're going to need that heat pipe to carry. This is pretty critical because it's going to determine the actual heat pipe diameter as well as the wick structure on the inside. We need to understand the orientation that you're going to be using your device in order to understand how the heat pipe needs to be routed and if it needs to operate against gravity or gravity aided. Quick definition here, when your heat pipe heat input or evaporator is lower in plane than your condenser, that's a gravity aided orientation. This means that the condensate from your condenser is going to return to your evaporator gravity aided. When we flip that and my heat source is now above the plane of my condenser, now it's against gravity orientation where my fluid return from my condenser to my evaporator is going to fight against gravity as it comes back. The thermal resistance for a properly designed heat pipe will not change whether it's operating gravity aided or against gravity. What will change is the transport capacity for that pipe, and we're going to talk about that in a moment. Next, it's important to understand some of the system level considerations. For instance, device maximum operating or maximum junction temperature, the maximum ambient temperature or external temperature in which you want to operate your device, and any non-operating temperature range requirements. This is again for items such as storage or transport. Let's now run through a quick example of how you can size a heat pipe for yourself. Here at Advanced Cooling Technologies, we do have a free online tool to help you in the design and sizing of these heat pipes. We're going to take a quick look at this little example put together. You can imagine an enclosure with a source on the inside, and you'd like to dissipate the waste heat from that source to a heat sink on the top of this enclosure. Given that we have about 6 inches between the chip and the chassis outer wall, we understand how much contact we can make with that heat pipe and the delta change in height, the delta H, I'll say, between the source and your heat sink. So if we say that this chip is generating about 70 watts worth of thermal waste, and we believe that the chip should be operating, or that device should be operating between about 60 and 70 degrees C when all is said and done. So the first step is you'd go online to one-act.com. In our resources tab, there is the heat pipe calculator. So when you click on this, you'll get a chart with a few inputs that you need to provide. Nominally the heat pipe length, the length of the evaporator, the length of the condenser, and the height against gravity. We've noted height against gravity as a negative number on this slide since the example I showed on the previous page is operating gravity aided. Once you input these and click submit, what you'll get is an output that looks very similar to the chart on the right side of the slide. What we're looking at here is the transport capacity, the Qmax, of a heat pipe as a function of its operating temperature on my x-axis. Their curves correspond to different outer diameters of heat pipe that we sized for you. So if we call up the previous example where we want to move 70 watts of waste heat operating between 60 and 70 degrees C, what we'll find is that between 60 and 70 degrees C, it looks like one 6-millimeter heat pipe, so that's the blue curve above the 70 watt line, or two 1/8-inch, which is the red line significantly below, will make up the total amount of power required to carry that 70 watts. So this is a good example of how you can use one heat pipe that can carry more than the amount of power, or you could use two smaller heat pipes to make them package better that can carry the total amount of power. So now that we've determined the appropriate outer diameter for the heat pipe that we want to use, and we've confirmed that it can move the amount of power, the next step is to design it into our assembly. You can bend and flatten heat pipes. Up on the slide here, you see some design guidelines. These are presented as pretty conservative guides for both bending and flattening. To bend a heat pipe, we recommend a bend radii greater than 3 times the outer diameter of the heat pipe. So for a 6-millimeter heat pipe, that'd be an 18-millimeter bend radii taken from the center line radius. To flatten a heat pipe, you can flatten a heat pipe down to 2/3 of its original outer diameter without impacting its transport capacity. What that means is you can take a 6-millimeter heat pipe down to 4 millimeters flattened and have it still move the amount of power that the 6-millimeter showed you on the chart. We can bend and flatten heat pipes beyond these limits. What we need to make sure is that the wick structure on the interior of the heat pipe stays attached to the wall so that we don't destroy the heat pipe's function. That would be taken on a case-by-case basis as needed. In terms of attachment, you can use epoxies or solder to attach your heat pipe to the next level assembly. Epoxy has inherently a lower thermal conductivity, so you're going to pay a higher delta T at those interfaces. If you have very high heat flux going through this heat pipe, that additional conductivity hit may create a large delta T. The more accepted way is to use solders. Solders are preferred by defense and aerospace applications, and they do not give you the thermal penalty that an epoxy would. One thing to keep in mind in designing a heat pipe system is that interfaces are critical. Sometimes when we see a system where the heat pipe may not be operating, or the customer believes the heat pipe may not be operating, what we find more often than not is it's one of the interfaces between the heat pipe and the next level assembly, the heat pipe, the evaporator, the heat pipe, the condenser, that is causing a large delta T to occur. So we have to get the heat into the heat pipe in an efficient way in order to in order for it to move its power in an efficient way. So now I'd like to pause to ask the webinar audience a quick question. Let's bring the poll up on screen. And the question is, what is your favorite technology publication? Magazine, blog, website? Please let us know. Thank you. Now back to our presentation. So for this next section, we'd like to talk about heat spreading and heat pipes used in assemblies to help with heat spreading problems. So the crisis that we see when we talk about high power devices is that the package size for your FPGA, your power amplifier, your ASIC, whatever it is that's creating that thermal load, the package size itself is shrinking while the total power is going up. Now, the efficiency of that device may have gone up as well, but it still leads in most cases to higher heat fluxes coming off devices than we've traditionally seen. These high heat fluxes create large hotspots that are going to impact the device performance. Traditional materials, such as copper, aluminum, magnesium, are again falling short of the thermal conductivity required to spread these loads efficiently. High K plates are essentially where we take a base metal, such as aluminum, copper, magnesium, and we embed into it high thermal conductivity heat pipes. This gives us now an aluminum plate, for instance, with embedded heat pipes would have an effective conductivity somewhere between 500 and 1200 watt per meter Kelvin. That's double or triple that of copper with the same weight as aluminum and similar strength as aluminum. Since we are embedding these heat pipes into these plates, we're bending and flattening them and ways to avoid all critical mounting features and ancillary features. And we can make these plates as thin as we can make a heat pipe, which is about 1.8 millimeter. On this next slide, we're looking at a plate that was designed for an application in which it was edge-cooled. So in the thermal charts on the left side of here, you see blue lines. The boundary condition is that these are locked into a liquid-cooled rail held at 32C. Even with those rails held at 32C, on the very left image, which is all aluminum, you can see the three devices that were creating local hotspots on this plate. What we did is by embedding heat pipes into that plate, the traces which you can see in the middle and right images, we've reduced the temperature that those devices are seeing by about 20 to 30 degrees by better spreading the heat along those liquid rails, increasing the efficiency of heat transfer there, as well as moving and spreading the heat throughout the plate, making more use of the thermal mass available to us. On the very right side, you see the plate that was actually manufactured with the heat pipe traces. Next, I want to take a little case study and pick this apart for you. We wanted to show that not only can high K heat sinks improve the efficiency of these systems, but they can also help reduce their size and mass. So we took a 100-watt source and we placed it on an extrusion that you can get off the shelf. This is an extrusion, aluminum extrusion, 6061, that you'd likely see on top of an electronics device, on top of a large PC board, fairly rudimentary. Then what we did is we calculated that we can achieve the same thermal performance for this heatsink given the same airside boundary conditions by embedding heat pipes into it. And we can also reduce the weight and the footprint of this heatsink significantly, which is exactly what we did. This next slide shows those two heat sinks under load in a FLIR camera, a thermal image showing that the maximum temperature is the same on each with the same boundary conditions, although the assembly on the right, the high K heat sink, weighs 33% less. So again, not only can heat pipes embedded in these high K plates help you move and spread your heat, you can also think of it in the different way, which is that now that I can move and spread my heat better, even if I didn't have a thermal problem before, I might be able to reduce the size of my assembly, reduce the size of my heat sink, helping me package everything better. There are a variety of ways heat pipes in these high K assemblies can be implemented into your system. As we just discussed, high K heat sink is a great way to move and spread heat throughout your fins, getting better fin efficiencies. High K board frames are used in a lot of standard VPX, VME type applications where a PC card's skyline and the devices populating that skyline are made to contact one of these boards. Heat pipes are routed through the board to move the heat from those locations to the edges. And also heat pipes can be used in larger chassis and sidewall type applications, again, moving and spreading heat in instances where traditional aluminum and copper just don't have the thermal conductivity or will create too high of a resistance to meet your ultimate thermal goals. So it's time now for our second and last audience poll. Let's bring that question up on screen. What are your favorite ways to learn about new technologies? Technical paper, short video, webinar? Please answer below. Thank you. Now on to the last section of our presentation. Here we're going to talk about the final passive technology that we feel is important in the design of these systems, and that is phase change materials. But first, let's introduce the problem that we think phase change materials solve. In some applications, your device, your source, only needs to be on for a short period of time. This may be a pulse load from a directed energy application or a transmit-receive burst from a power amplifier. Electronics that operate with this type of transient heat load in which you have some off-cycle are good candidates to benefit from a phase change material system. At the top level, a phase change material system is a thermal battery or a thermal capacitor used to absorb that transient load when it's happening so that it can be dissipated. But first, what is the phase change material itself? So these PCMs take on a variety of form. Most of the ones that we use here at ACT are paraffin-based waxes. There are also non-paraffin organics that can be used, hydrated salts, which have some instabilities, as well as full metallics for very high density. The phase change material itself is put within some type of a hermetic enclosure, and that's what gives its thermal capacitance. These materials have large latent heat, but unfortunately they have very low thermal conductivity. So this makes the design a somewhat interesting process. Let's talk about what that looks like. So the typical design process for a phase change material heatsink is first to look at the total thermal load that the heatsink is going to need to absorb. This is a fairly quick calculation. Again, you can figure out the heat capacity of the phase change material, and you can determine the total amount of power that you're going to want to store within this system, and calculate the number of grams, kilograms of phase change material that would be required. That's the simple part. Unfortunately, due to the low conductivity of these materials, we typically need to design some type of a structure internal to spread that heat and move it and ensure that we're melting efficiently. The trade-off between the internal structure and the amount of phase change material is just that. You're going to have a trade-off between the thermal gradient produced through that heatsink and the PCM volume. Less fin structure on the inside of the heatsink can lead to more phase change material, which will have a longer melt time associated with it at the cost of a higher delta T through the system. As we go back and forth on that fin design and thermal analysis to ensure that we're meeting the thermal goals, we'll iterate on that, complete the detailed structural design, including how to actually seal that phase change system, and then move to a final design where it's ready to manufacture. ACT does have some online tools for looking at phase change heat sinks and trying to understand how large that system needs to be and the approximate delta T that you'd see throughout. These are, again, free tools online that we'll have links to. So a quick summary for phase change material heat sinks is that they work as thermal batteries or thermal capacitors to absorb transient loads within systems. The internal design, specifically the fin structure, is critical to efficiently make use of your system and all the volume of PCM. And a lot of the applications are still developing. So we see a lot of, again, single-use devices, a lot of directed energy applications with high loads and long off cycles. But there's a myriad of other applications that we have customers reaching out to us to try to scope and design to. Finally, I'd like to do a quick review of some of the different technologies we've talked about today and where they might be used. If your application is such that you are getting away and meeting your thermal goals via conduction through base metals, such as aluminum, copper, magnesium, that makes the most sense. Those systems inherently are the most simple, and certainly we would recommend that direction as well. When you need to transfer that power, and conduction will work, but you need some type of a flexible joint, looking at thermal straps is another way to solve your problem. A thermal strap is essentially a braided form of that base metal that has some flexibility to it. When you begin encountering heat fluxes that are higher and thermal loads that are larger, then the base metal is going to allow for or will create a large delta T through that base metal. Now you can consider heat pipes. Again, a heat pipe, due to the two-phase heat transfer occurring internally in a closed system, are capable of much higher thermal loads and can move that load from source to sink with very low thermal resistance. The high K plate is another permutation of a heat pipe. Now we're taking those and embedding them into the base metal plates themselves. This allows us to do a lot of heat spreading. This also allows us to incorporate these heat pipes into the bases of heat sinks to improve fin efficiencies. And finally, in transient thermal load applications, phase change material can be integrated into these heat sources, into these heat sinks, in order to dampen the load, such that now you can design the system for the average power instead of the peak power, and or they can be used to simplify the design of the thermal solution in one-time use devices. ACT has a variety of resources to help you help yourself in the design and implementation of these types of passive solutions. We really want to make you knowledgeable in the subject and help you move forward with your design. So please reach out to us and or use our resources as needed. I'd like to thank you for your time and throw it back to Lisa.
Oh, thank you, Dennis. That was an excellent presentation. We'll now begin the Q&A. Answering questions today is Lead Product Development Engineer Ryan Spangler. Ryan, your first question is a multi-part question related to PCMs. First, how much additional volume needs to be allocated to compensate for the solid to liquid phase transition in a PCM heatsink? Next, how is the melting temperature controlled? And finally, how does the PCM degrade and how many cycles is typical? Ryan?
Very good question. So in terms of how much additional volume should be considered, we generally recommend anywhere between 10 to 15%, just based on the expansion as it goes from a solid state to a liquid state. Since I'm fairly conservative, I would say just outright assume 15%. And with your design, you can assume that we're going to get some additional PCM in there that you hadn't previously anticipated, which tends to be a good thing. In terms of the melting temperature, that's controlled mainly by the selection of the material used. for the phase change. So Dennis pointed out a few different options as he went through his presentation. Paraffin wax are very common and tend to melt in a range that's used as max temperature or operating temperatures of typical electronics. So those are very common. If you start getting too hot, you start moving into the metal phase change materials. You can cheat a couple degrees just based on changing some thicknesses of your enclosure itself, but the drastic changes and really fine-tuning that occurs just based solely on the material selection. And does the PCM degrade? How many cycles is typical? That's a great question. I'm inclined to say nothing lasts forever, right? So the better question is how many cycles do you need to see for that material? So depending on that, if you're a one-and-done situation, you're probably not so concerned about this question. If you're using it for a missile or something, you might have a few cycles worth of ground testing, but other than that, it needs to work once, and you'll never see it again. In opportunities where you need a couple hundred cycles, we might recommend one of the organic blends that sustains its properties up through the low hundreds to high hundreds worth of cycles, and you start seeing some decay or degrading as those separate. And then there's some very pure, just long chain hydrocarbons that are available in the market, and those will last you through tens of thousands of cycles without any noticeable degradation.
Thanks, Ryan. Very, very good. Your next question is a two-part question. First, how does the heat pipes perform in a microgravity environment, and what does the typical qualification and/or testing look like for these environments? Ryan?
All right, that's a fairly loaded question. So first and foremost, the microgravity environment, I would say they perform well, and that's mainly because typical wicked heat pipes don't rely on a gravity head to operate. They rely on the capillary pressure that's being generated by that wick structure. So all the physics inside of it are driven by various pressure drops throughout the system, your liquid, vapor pressure drops, and then overall your capillary pressure drop. So they perform very well. It's comparable to doing basically a horizontal ground test where you take most of the gravity head away from the situation. The typical testing qualification test regimens are, I would say, heavily contingent on which technology you're looking at. For instance, our standard aluminum, ammonia, constant conductance heat pipes are a linchpin in space flight technologies. They've been used since, I believe, the 60s. Everything's very well defined in various specifications. It's a very safe technology from the space community's perspective to use. For instance, we actually have over 40 million hours, I believe, on orbit without a failure. So that just speaks to the processes that have been established and refined throughout the years to give you something very robust and reliable. So the typical testing might be a couple of thermal performance checks throughout the process, maybe some pressure checks, make sure that you're able to hold back the vapor pressure of the ammonia as it operates, and maybe a non-condensable gas check where you just burn it in for a short amount of time and see if there's any sort of internal reactions, if it wasn't cleaned well enough, that might generate gas. And those are all typically lot-based. And again, since it's a very well-established technology, the qualification testing is what we consider to be more a qualification by design. So we go through and each new design, we will do the same thermal performance checks, maybe additional temperatures, powers, etc., really define the performance of the extrusion selected. We'll maybe do some shock and vibration, burst pressure tests, just to verify that, where will that envelope truly fail. But all things considered, once it's passed and through its qualification testing, you don't have to repeat it. Now, that's contrary to one of the newer technologies that's being adopted in the industry in copper water heat pipes, as was presented on here. That's been very common for terrestrial use through the years, and it's now being, as I said, adopted for space flight. being a newer technology, it tends to fall under a lot-based type qualification, as well as you have water as a working fluid, and it goes up to space where your systems tend to run cold whenever you're in eclipse. Water obviously expands as it freezes, so one of the main concerns or tests that we see are environmental-based, putting some proof of concept thermal freeze-thaw cycles on the systems, powered freeze-thaw, what happens whenever power is being applied as the system goes to a frozen condition, and all that working fluid wants to depart from the evaporator and condense and freeze in the condenser. So wick degradation plays a huge role. You need to be very sensitive of the amount of fluid charge that you're putting into the system. There are certain design aspect ratios that need to be taken into consideration. So there's a lot to be said there. We do have some standard tests that we recommend being run for those systems. And that, again, if you reach out to Dennis and his team, we can have some conversations about what environments you are expecting and what we would recommend to make sure you're getting a good product at the end of the day.
Thanks, Ryan. Someone wants to know, what other temperature ranges can heat pipes operate in?
Good question, and this will be a short one. Really, you can go all the way from the cryogenic temperature ranges to the very hot, 1,000+ degrees Celsius temperature range. So the common working fluids that I've seen are the ammonia-based systems, water. Sometimes you'll dabble in some methanol, which kind of envelopes water and ammonia, or is enveloped by those. As you go very cold, you'll start getting into ethane and methane temperature ranges, or even lower are, you're starting to get to helium. You get really hot, and you'll start looking at sodium, potassium, those types of working fluids. And for all those situations, a lot of thought needs to be put into the material compatibility. So making sure you have the appropriate envelope selected is very important.
And the next question, how expensive is a high-K heatsink?
That is the question. So very, very difficult one to answer. It's going to depend on the quantity and complexity of the system that we're looking at. As Dennis said in his presentation, if you have an opportunity where you can get away with a copper or aluminum heatsink only, and you're not worried about your mass of that copper heatsink, we'd always recommend to go that route. It's going to be cheaper, and it's going to work well for you. Once you start getting to the higher heat loads, that's where copper water heat pipes start coming into play. And compared to other advanced thermal management techniques, they tend to be cost effective. One other place where it might make sense is if you can get away with, let's say, the conductivity of copper for a heatsink, but you just can't deal with the mass impact, embedding heat pipes into an aluminum body will have a comparable mass to just an aluminum heatsink, while having bulk effective conductivities well in excess of aluminum and generally higher than copper as well, if it's designed well. So I would say if you're interested in getting a cost point where it makes sense, you reach out to Dennis and his team, and they'll spin up some numbers for you.
Good advice. And with that, we're at the end of our webinar. I thank Dennis Pamukchu for today's presentation and Ryan Spangler for answering these questions. Questions not answered during today's webinar will be addressed by email after the webinar. I want to also thank our audience for watching today's webinar, which will be available soon on our website. You'll receive an email when the archive is ready. If you would like a copy of today's slides, you may download a PDF of them under Event Resources on your screen. Lastly, I want to mention that a survey will pop up on everyone's screen in a few moments. Please share your thoughts with us by answering just 3 questions. Thank you.